Right now, something is wrong with the universe. The force pushing every galaxy apart is getting weaker. For years, scientists swore it was constant, a steady pressure that would spread the cosmos thin forever. New data broke that idea wide open. We'll see the machine in Arizona that caught it, particles that shift shape in empty space, and the day all of space could come crashing back. If a good mystery keeps you up at night, subscribe. Take a breath. We begin. Look up on a clear night, and the stars seem nailed in place. Same shapes your grandparents saw. Same shapes the ancient Greeks drew into pictures. Steady, quiet, forever. That picture is a lie. Every single galaxy out there is running away from us. Right now, as you read these words, the space between us and them is stretching, and they are sliding off into the dark. The faraway ones move fastest, like they are scared of something. For most of history, nobody knew this. People looked up and felt small but safe. The sky was a ceiling, a painted dome over a still world. Then one man pointed a telescope at the smudges between the stars and started doing math that broke that ceiling apart. His name was Edwin Hubble, and in the 1920s, he was staring at faint blurs of light that other astronomers called clouds. He proved they were not clouds at all. Each one was a whole galaxy, a city of billions of stars, sitting unbelievably far away. Picture finding out that every dust speck on your bedroom floor is actually a packed stadium full of suns. That was the size of the shock. Then he noticed something stranger. He measured the light from those galaxies, and almost all of it was stretched toward the red end of the rainbow. Light does that when its source is moving away from you. A train horn drops in pitch as it speeds past. Galaxy light does the same thing, only with color instead of sound. So the galaxies were fleeing. Every direction he looked, they ran. Here is the part that messes with your head. They were not running away from one center, like sparks from a campfire. They were spreading apart from each other, all at once, everywhere. The whole stage was getting bigger. Think of a balloon with dots drawn on it. Blow it up, and every dot drifts away from every other dot. No dot is the middle. No dot stays still. The skin between them just keeps growing. That balloon skin is space itself, and we are one of the dots watching all the others slide off. This was the first crack in the old story. The universe was not a calm, the finished room. It was a thing that was happening, expanding, moving, alive in a way nobody had pictured. For a while, scientists made peace with it. Fine, they said. The universe is growing. It exploded into being long ago, and it has been coasting outward ever since, like a ball rolling across a field. And just like a rolling ball, it should be slowing down. Gravity from all that matter should be pulling everything back together, tapping the brakes on the whole show. That made sense. It felt right. The expansion was real, but gravity was the boss, and gravity always wins in the end. The only question left, people figured, was simple. Would the brakes stop the universe gently, or would they yank everything back into a giant pile-up someday? They built better telescopes to find out. They aimed them at the oldest, faintest light they could catch, hoping to measure exactly how fast the cosmos was hitting the brakes. In 1998, they got their answer. It was the opposite of everything they expected, and it came from the light of stars that were already dead. To check the speed of the universe, scientists needed a special kind of lighthouse. A flash so bright and so regular that they could spot it across unthinkable distances and know exactly how far it sat. They found it in dying stars. When a certain type of star runs out of fuel and explodes, it always blows up with nearly the same brightness, every time. These blasts are called Type 1 supernovas, and astronomers love them for one beautiful reason. If you know how bright a flash truly is, and you measure how dim it looks from here, the difference tells you the distance. A candle across the room looks bright. The same candle a mile away looks like a pinprick. Same candle, different glow, easy math. So a star explodes in a galaxy billions of miles away. For a few weeks, it shines as bright as 1 billion suns, outshining its entire home galaxy. Then it fades. Telescopes on Earth catch that fading light, and from it, scientists can measure both how far the galaxy is and how fast it is rushing away. Two teams of researchers were racing to do exactly this in the 1990s. They were rivals, hunting the same prize, both convinced they would catch the universe slowing down. Their whole plan was simple: find the most distant exploding stars they could, compare them to closer ones, measure how much the brakes had kicked in over billions of years. They expected the faraway explosions to look a little too bright. That would mean those galaxies were closer than the expansion rate suggested, which would prove the universe used to fly apart faster and had been slowing down ever since. The light came in. The teams crunched the numbers, and the distant supernovas were wrong. They were too dim. Not a little dim, clearly, stubbornly, impossibly dim. The faraway galaxies were farther than they should have been. The only way that made sense was if the universe had not been slowing down at all. It had been speeding up. The expansion was getting faster every year, like a car flooring the gas pedal on an empty highway with nobody touching it. Both teams stared at the same crazy result. They checked it. They tore their own work apart looking for a mistake. There was dust to worry about, faint dust between galaxies that could dim light and fake the whole thing. They hunted for it. They ruled it out. The answer would not go away. One of the lead scientists later said he was sure he had made an error because the result felt too strange to be real. A speeding up universe meant something was pushing outward, harder than gravity could pull. Something with no name. Something nobody had ordered. Both rival teams published in the same year, 1998. They had been trying to beat each other, and instead they handed the world the same earth-shaking news. The universe is not coasting to a stop, it is accelerating. A force was loose in the cosmos, fighting gravity and winning, stretching space faster and faster across distances so wide that light takes billions of years to cross them. Nobody had the faintest idea what it was. They could measure it, they could prove it was there. They just could not see it, touch it, or explain it. So they gave the mystery a name, and that name would haunt physics for the next 30 years. They called it dark energy. The name is almost a confession. Dark, because it gives off no light, no heat, no glow of any kind. Energy, because something is clearly doing work, shoving galaxies apart with a strength that beats gravity across the whole sky. Put those two words together, and you basically get a label that means, we know it is there, and we have no clue what it is. Here is the fact that should stop you cold. This stuff you cannot see, cannot feel, and cannot catch is the main ingredient of the entire universe. It makes up around 70% of everything that exists. 7 out of every 10 parts of reality is this invisible push. Sit with that for a second. Every star you have ever seen, every planet, every galaxy in every photo, all of it together is the small slice. The mystery force is the big slice. We have been studying the universe for thousands of years, and we somehow missed the part that runs the place. Picture a giant glass jar that holds everything in existence. Fill 70% of it with a clear liquid you cannot see, smell, or touch. Then drop in a few grains of glitter, scattered thin. The glitter is every galaxy, every sun, every world. The invisible liquid is dark energy, and it is pushing the walls of the jar outward, making the whole thing bigger every second. What makes dark energy so spooky is how it behaves backward from everything else we know. Normal stuff pulls, gravity grabs. Two objects with mass drift toward each other, the way the moon hugs the earth and the earth hugs the Sunday. The more matter you pile up, the harder it all yanks inward. Dark energy does the opposite. It pushes, it pries things apart. And the weirdest part is that it does not weaken as the universe grows. A campfire fades as you walk away from it. A speaker gets quieter down the hall. Dark energy refuses to follow that rule. As space stretches and galaxies get farther apart, the push does not die down. By the old standard idea, it stays exactly as strong as ever, filling every new gap the moment that gap appears. That means the universe is locked in a strange tug of war. Gravity is trying to pull all the matter back together. Dark energy is trying to rip it all apart. For the first several billion years, matter was packed tight, so gravity was winning, slowing the expansion down. Then space spread out enough that the matter thinned, gravity loosened its grip, and dark energy took over the fight for good. We are living in the era when the push is beating the pull. That is why the galaxies are speeding up instead of slowing down. The invisible giant grabbed the wheel, so scientists had a force they could measure but not explain. A thing that fills space, pushes outward, and never fades. The obvious next question was the hardest one of all. What actually is it? Where does it come from? What chunk of physics could possibly create a force that hides in empty space and overpowers gravity across the entire cosmos? The strangest part is that the answer might have been written down decades earlier, by accident, by a man who threw the idea in the trash and called it the dumbest thing he ever did. Go back to the year 1917. The First World War is grinding across Europe, and a 37-year-old physicist named Albert Einstein is sitting with a problem that has nothing to do with the war and everything to do with the shape of the entire universe. He had just finished the work that made him a legend, his theory of gravity. It described gravity not as a simple force, but as a bending of space and time itself. Heavy objects warp the space around them, and other things roll along those curves. The sun makes a dip, and the earth circles inside it like a marble rolling around a bowl. The math worked. It predicted things older theories could not. It was, by any measure, a masterpiece. Then Einstein pointed that math at the whole universe at once, and it gave him an answer he hated. His own equations said the universe could not be sitting still. All that matter, all those stars pulling on each other through gravity, should be falling together. The cosmos should be collapsing into one giant clump, or it should be flying apart. Either way, it could not just sit there, calm and unchanging. This bothered him deeply, because in 1917, everyone, Einstein included, believed the universe was exactly that: calm, fixed, eternal. The galaxies running away had not been discovered yet. Hubble was still years from his big find. As far as the smartest people alive knew, the universe had always been there, would always be there, and never changed. So, Einstein faced a choice: trust his equations, which screamed that the universe must be moving, or trust the common belief that it was standing still. He blinked. He chose the belief. To force his math to describe a still universe, he added a new piece to his equations by hand. A little fudge factor, a term that acted like a gentle outward push, just strong enough to cancel gravity and hold everything in a frozen balance. He called it the cosmological constant. It was a number he basically invented to make the universe behave the way he expected it to. It was a patch, a bit of duct tape over a result he did not want to believe. The push had no source he could explain. He just needed it to be there, so he wrote it in. Then 1929 arrived. Hubble announced that the galaxies were flying apart. The universe was not still at all. It was expanding. Exactly the kind of motion Einstein's raw equations had predicted before he taped them down. Einstein had been right the first time, and he had talked himself out of it. If he had only trusted his own math, he could have predicted the expanding universe years before anyone saw it. Instead, he had buried that prediction under a fudge factor invented to protect an idea that turned out to be wrong. He pulled the cosmological constant out of his equations and threw it away. He reportedly called it the biggest blunder of his life. For decades, physicists agreed. The cosmological constant was a famous mistake, a cautionary tale about even genius getting spooked. Textbooks mentioned it the way you mention an embarrassing old photo. It was dead, buried, and laughed off. It should have stayed in the grave. But the very thing Einstein invented and erased, that mysterious outward push baked into space, was about to come crawling back, decades later, wearing a brand new name. For nearly 70 years, Einstein's fudge factor stayed buried. Physics had moved on. The cosmological constant was a footnote, the answer to a trivia question about the one time the great man got it wrong. Then came 1998, and those two rival teams with their dying stars and their impossible result. The universe was speeding up. Some force was pushing space apart, harder and harder, with no visible source. The physicists chasing this new mystery needed a way to describe it in their equations. They needed a math term that could sit inside empty space and push outward without fading. And somebody noticed something that must have felt like a ghost walking into the room. That term already existed. It was the cosmological constant, the exact piece Einstein had invented out of thin air and then thrown away in shame. The thing he created to hold the universe still turned out to be the perfect tool for describing a universe flying apart. He had built the right idea for the wrong reason, then deleted it, and now it was clawing its way back into the heart of physics. The blunder was not a blunder, it was an accidental prophecy. Here is the beautiful, frustrating twist. Einstein added his constant to stop the universe from moving, but the same math term, with the dial turned the other way, does the opposite job perfectly. Instead of holding everything in a frozen balance, it can shove everything apart, faster and faster. Same idea, same equation, just cranked toward push instead of standstill. So the modern story of dark energy starts with a man undoing his own genius. If Einstein had left his constant alone, if he had just trusted the math instead of the mood of his time, he might have been ready for the speeding up universe before it was even found. Instead, the world had to stumble onto it the hard way, decades later, through the fading light of exploded stars. The return of the cosmological constant gave scientists their first real way to explain dark energy. The simplest idea was this: dark energy is the cosmological constant. It is a fixed property of space, the same everywhere, the same in every era, a steady outward pressure built into the fabric of reality. Empty space is not truly empty. It carries a tiny, constant push, and across the unimaginable size of the universe, those tiny pushes add up to a force that beats gravity. This idea became the backbone of the standard model of the cosmos. Scientists gave it a name that sounds like a spaceship, lambda CDM. The lambda is the Greek letter standing in for Einstein's constant. For years, this model worked shockingly well. It predicted how galaxies should clump, how the oldest light in the sky should look, how fast everything should fly apart. Check after check, it passed. It became the foundation, the bedrock, the thing nearly every astronomer built their work on top of. Dark energy was a constant. The universe would expand forever, smooth and steady, growing colder and emptier until the end of time. Everyone got comfortable. The mystery had a shape, even if it had no face. The math behaved. The future of the universe looked settled, if a little lonely. There was only one problem with this tidy picture, and it was an ugly one. When scientists tried to calculate exactly how strong that constant push of empty space should be, the number they got back was so wrong, so insanely far from reality, that it became known as the worst prediction in the history of science. To understand why the prediction went so wrong, you first have to understand a strange idea. Empty space is not empty. When you picture a vacuum, you imagine pure nothing. No air, no light, no particles, just a black void. Scoop out every atom from a box, and you would call what is left empty. That is how it looks. That is how it feels. That is also wrong. Down at the smallest scales of reality, empty space is boiling. Physicists discovered that the vacuum is alive with tiny flickers. Particles pop into existence, exist for the briefest flash, then vanish again, over and over, everywhere, all the time. They are called virtual particles, and they blink in and out so fast you can never catch one directly. Think of the surface of a pot of water just before it boils, trembling with tiny bubbles that appear and burst in an instant. Now shrink that down smaller than an atom and spread it through every speck of space in the universe. That is the vacuum. This constant fizzing carries energy. Energy is woven into the empty space itself, even when nothing else is around. Scientists call it vacuum energy, and it gave them a thrilling idea. What if this is dark energy? What if the push that drives galaxies apart is just the energy of empty space, the leftover hum of all those flickering particles? It fit perfectly. Vacuum energy would be everywhere, since empty space is everywhere. It would never fade, since space keeps making more of itself as it expands. It would push outward, exactly the behavior Einstein's constant described. The pieces snapped together. For a moment, it looked like physics had cracked the whole thing open. Then they did the math. Quantum theory, the rulebook for the tiny world, lets you actually calculate how much energy should be packed into the vacuum. So they calculated it. They added up the contributions from all those flickering virtual particles and asked the equations, how strong should this push be? The answer came back enormous, gigantic beyond all reason. The math said empty space should be crammed with so much energy that the universe would have blown itself apart in a fraction of a second after it began. Galaxies could never have formed. Stars could never have lit. You could never have existed. The push would have been so violent, it shredded everything before anything could take shape. Then they measured the real value out in the actual cosmos, using the speeding galaxies. The true strength of dark energy is tiny, a faint, gentle push, just enough to win against gravity over billions of years. Now compare the two numbers. The predicted value and the measured value, they do not miss by a little. They do not miss by 1,000 times, or 1,000,000, or even 1,000,000,000. The theory overshoots reality by a 1, followed by around 120 zeros. It is the largest gap between prediction and measurement anywhere in all of science. Physicists call it the vacuum catastrophe, and the name is not for show. It means something is deeply, badly broken in our understanding. The best theory of the tiny world and the best theory of the cosmos give wildly different answers about the same simple thing, and nobody can explain why. If dark energy really is the energy of empty space, then we are off by an amount so absurd it should embarrass the whole field. Which forces a darker question. Maybe dark energy is not the energy of empty space at all. Maybe it is something we have not even imagined yet. The vacuum catastrophe left physics with an open wound, off by a 1 followed by 120 zeros. That is not a small error you patch later. That is a sign that something at the foundation is wrong. Scientists tried everything to close the gap. Some suggested that unknown particles might cancel out most of the vacuum energy, leaving only the tiny push we see. The math for that almost worked, but it needed the cancelling to be perfect to an absurd number of decimal places, like balancing a pencil on its tip and having it stay there for 1,000,000,000 years. Possible, in theory, insane in practice. Others wondered if we were simply measuring something we did not understand. Maybe dark energy was real but came from a source nobody had written equations for yet. Maybe the vacuum idea was a dead end dressed up as an answer. The honest truth was uncomfortable. The leading explanation for the most powerful force in the universe produced the worst number in the history of physics. Scientists were using a model that worked beautifully for predicting how galaxies move, while the engine inside that model made no sense at all. This is the part people outside science rarely see. A theory can be useful and broken at the same time. Lambda c, d, m, the standard model of the cosmos, kept passing its tests. It described the real sky with stunning accuracy. Yet at its heart sat this constant push that, when you asked where it came from, gave answers off by more zeros than there are atoms in your body. So, a quiet split formed among physicists. One camp said, "The model works. Stop worrying. The constant is just a fact of nature we have to accept, even if we cannot derive it. The universe simply has this tiny push baked in, and asking why is like asking why the speed of light is what it is. It just is." The other camp could not let it go. A number that wrong, they argued, is the universe screaming at us that we are missing something huge. You do not ignore an error of 120 zeros. You chase it. Somewhere in that gap, they believed, was a discovery bigger than dark energy itself, a clue about how the tiny world and the giant world actually connect. Both camps agreed on one thing. To settle the argument, they needed better data, way better. The supernova measurements from the 1990s had proven dark energy was real, but they were rough, like sketching a face from across a dark room. To truly understand the push, scientists needed to measure it across the whole history of the universe. They needed to know not just how strong dark energy is now, but whether it has changed over billions of years. Because here is the question that everything hinged on. Is dark energy truly constant, the same yesterday, today, and forever, exactly as Einstein's old fudge factor demanded? Or does it shift, grow, and fade over time like a living thing? If it was constant, the standard model survived, ugly number and all. If it changed, even a little, then dark energy was not Einstein's constant. It was something new, something dynamic, something with its own behavior and its own story. And the entire predicted future of the universe would be thrown into doubt. To answer that, you cannot stare at a few exploding stars. You have to map millions of galaxies across billions of years. You have to build a machine powerful enough to read the history of the cosmos itself. In a desert in Arizona, scientists were doing exactly that. But before we follow the light up to the stars, we need to talk about the other invisible giant hiding in the dark. Dark energy is not the only ghost in the universe. There is a second invisible thing, just as strange, just as hidden, and it was actually discovered first. It is called dark matter, and the story of how we found it is a story of things that should fall apart but somehow do not. Back in the 1930s, an astronomer named Fritz Zwicky was studying a giant cluster of galaxies, a huge swarm of them swirling around each other in deep space. He measured how fast those galaxies were moving, and the numbers made no sense. They were whipping around so fast that the cluster should have torn itself to pieces. There was not nearly enough visible matter, not enough stars and gas to hold it together with gravity. By all rights, those galaxies should have flung off into the void like riders thrown from a spinning ride. But the cluster was not flying apart. Something was holding it together. Something with a lot of gravity that gave off no light at all. Most scientists ignored Zwicky for decades. He was a difficult man with a wild idea, and the evidence was thin. Then, in the 1970s, an astronomer named Vera Rubin found the same ghost in a different place, and this time, it could not be brushed off. Rubin was studying how single galaxies spin. A galaxy is like a giant pinwheel of stars. Common sense says the stars near the edge should move slower than the ones near the center, the way the outer planets in our solar system orbit slower than the inner ones. That is how gravity works when most of the mass sits in the middle. She measured galaxy after galaxy. The outer stars were not slowing down. They were racing around just as fast as the inner ones, sometimes faster. It was as if the whole pinwheel were glued together by some hidden weight spread far beyond the glowing part. The only explanation that fit was unsettling. Every galaxy must be wrapped in a huge, invisible cloud of matter, far bigger than the bright disk we can see. Stars and gas are just the glowing core sitting inside a vast, dark halo. That halo has gravity. It pulls. It holds the speeding stars in place. We just cannot see it. That invisible stuff is dark matter, and it makes up about 25% of the universe. Add it to dark energy, and you get the gut punch. Around 95% of everything is invisible to us. The stars, the planets, the glowing galaxies in every gorgeous photo, all of it together is a thin film floating on top of an ocean of stuff we cannot detect. Dark matter does not push like dark energy. It pulls, like normal matter, with gravity. It builds the scaffolding that galaxies hang on. Without it, galaxies would never have formed in the first place. It is the hidden skeleton of the cosmos, holding the bright parts in shape We know it is there from the way its gravity bends starlight and grips spinning galaxies. We have mapped where it sits. We have watched it shape the largest structures in existence. And after almost 100 years of hunting, we still have never caught a single piece of it. That makes two great invisible giants. One pulls everything together, one pushes everything apart. Both are unseen, and both dwarf the visible universe, which leaves an uncomfortable thought about the part we can see. The stuff you are made of might be the rarest material in the entire cosmos. Here is a fact that should change how you see yourself in the mirror. Everything you can touch, taste, smell, or hold, every atom in your body, and every object you have ever owned, belongs to less than 5% of the universe. Ordinary matter, the stuff of stars and planets and people, is the smallest slice of all. Around 70% is dark energy. Around 25% is dark matter. Everything left over, the entire visible cosmos, scrapes in under 5%. Roll that number around in your head. Less than 5%. Every galaxy in every telescope image, every star that has ever burned, every world, every moon, every comet, every grain of dust drifting between the planets, all of it crammed into that thin final sliver. It gets stranger when you realize how spread out even that tiny slice is. Take ordinary matter, the small 5%, and look at where it actually goes. Most of it is hydrogen and helium, the two lightest, simplest gases, floating thin between the stars. The heavier stuff, the carbon in your cells, the iron in your blood, the oxygen you breathe, the calcium in your bones, makes up only a tiny fraction of that already tiny 5%. So the matter that can build something interesting, something alive, something that can look up and wonder about all this, is a sliver of a sliver of a sliver. You are not made of the common stuff of the universe. You are made of the rarest leftovers, the trace ingredients, the seasoning sprinkled on top of a cosmos that is almost entirely invisible. Think of the whole universe as a swimming pool filled to the brim. Dark energy is most of the water. Dark matter is the rest of the water. All the ordinary matter, every star and planet and person, is a thin film of oil shimmering on the surface. And the part of that oil capable of forming a living, thinking creature is a single drop. That single drop is you. This rare material has an incredible origin. The heavy atoms in your body were not made on Earth. They were forged inside stars, cooked under crushing heat and pressure over millions of years. When those stars died and exploded, they flung that material across space, where it eventually gathered into new worlds, including ours. The iron in your blood was once at the core of a star that blew itself apart. You are walking, talking stardust, built from the rarest scraps of an almost entirely hidden universe. That should not make you feel small. It should make you feel impossible. For most of human history, we thought we were ordinary, a small world in a big sky. Then we learned the sky was bigger than we imagined, and we felt smaller still. Now we are learning the opposite lesson. The visible, touchable, living part of the universe is the rarest thing in it, and we are made of the rarest part of that. We are the exception, not the rule, the strange flicker of light in an ocean of darkness. And to understand the dark ocean we are floating in, to finally measure whether its mysterious push is steady or shifting, scientists could not just think harder. They had to build something, a machine that could read the light of millions of galaxies and trace the entire history of the universe across billions of years. Out in the Arizona desert, on top of a mountain, that machine was about to open its eye. On a mountaintop in Arizona stands a dome that looks like an observatory from an old movie. Inside it sits a machine built to do something no human eye could ever attempt. It is going to map the universe in 3 dimensions, deeper and wider than anyone has mapped it before. The machine is called DESI, short for the Dark Energy Spectroscopic Instrument. Its whole reason to exist is one question: is dark energy steady, or is it changing? To answer that, it has to do something almost unbelievable. It has to measure the exact distance and motion of tens of millions of galaxies, building a map so huge it captures 11 billion years of cosmic history. 11 billion years. That is most of the age of the universe itself. The machine is not just photographing the sky, it is building a time machine made of light. Here is how that works, and it is one of the coolest tricks in all of science. Light travels fast, but space is so vast that light takes a very long time to cross it. When you look at a galaxy a billion light years away, you are not seeing it as it is now. You are seeing the light that left it a billion years ago. You are looking into the past, so the farther DESI looks, the deeper into history it sees. Nearby galaxies show the recent universe. Distant ones show it as a young thing, billions of years ago. By collecting galaxies at every distance, the machine builds a record of how the cosmos has grown and changed across nearly its entire life. It can watch dark energy at work in different eras, like flipping through a flipbook of the universe getting older. If the push has stayed exactly the same through all that time, the standard model holds. If the push was stronger or weaker in the past, then dark energy is changing, and the whole picture cracks. To pull this off, DESI tracks something called baryon acoustic oscillations, which is a mouthful, so think of it this way. In the first moments after the Big Bang, the early universe rang like a bell. Pressure waves rippled through the hot soup of matter, freezing in place a kind of pattern, a faint preferred spacing between galaxies. That spacing acts like a ruler stamped into the sky. By measuring how that built-in ruler appears to stretch at different distances, scientists can read exactly how much the universe has expanded at each point in its history. A cosmic ruler printed into the universe at its birth that DESI reads across billions of years. Stretch the ruler, and you measure the growth of everything. The challenge is the sheer scale. To map the universe with enough detail to catch a tiny change in dark energy, you cannot study galaxies one at a time. That would take longer than the universe has existed. You need to capture thousands of them at once, night after night, for years, until you have built a catalogue of millions. That is the part that sounds impossible. How do you measure the precise distance to thousands of separate galaxies in a single shot every single night with one machine on one mountain? The answer is hiding inside the dome, in a system so precise and so strange that it works more like a swarm of tiny robots than a telescope. Lift the lid on DESI and you find something that looks less like a telescope and more like a hive. Packed into the focus of the instrument are 5,000 tiny robots, each one gripping a single thin strand of glass fiber. And every night, those 5,000 robots come alive at once. Each little robot has one job: point its glass fiber at one specific galaxy, far out in space, and hold it there with incredible steadiness, while the machine drinks in that galaxy's light. 5,000 robots, 5,000 fibers, 5,000 galaxies, all captured in the same moment. Picture 5,000 tiny hands, each holding a straw, each aimed at a different sip of light coming from a different corner of the sky. That is what is happening inside the dome every clear night. The precision here is almost hard to believe. These robots have to position their fibers to an accuracy finer than the width of a human hair. A galaxy in the sky is a faint, distant smudge, and the fiber has to land on exactly the right spot to catch its light and nothing else. If the aim is off even slightly, the fiber grabs empty sky or the wrong object, and the measurement is ruined. Once the fibers are aimed, the light they catch gets pulled apart. The machine takes each galaxy's light and spreads it into a rainbow, the way a prism splits sunlight into colors. This spread out light is called a spectrum, and it is packed with hidden information. Remember how galaxy light gets stretched toward red when the galaxy is moving away from us. In the spectrum, that stretch shows up as a shift in certain sharp lines, like fingerprints in the colors. By measuring how far those fingerprints have slid toward red, DESI figures out exactly how fast each galaxy is rushing away, and from that, how far it sits and how far back in time we are seeing it. Do this for 5,000 galaxies a night. Then do it again the next night, and the next, for years. Slowly, point by point, a three-dimensional map of the universe takes shape. With each galaxy pinned in space and in time, the numbers pile up fast. In a single night, DESI can measure more galaxies than older surveys managed in years. Over its full run, it aims to map tens of millions of them, building the largest, most detailed chart of the cosmos ever made. Each galaxy is a single dot. Millions of dots together form a structure, a web of light stretching across the history of the universe. And inside that web hides the answer scientists are desperate for. By measuring how galaxies are spaced at different distances, by reading that built-in cosmic ruler across billions of years, DESI can finally test whether dark energy has held steady or quietly changed. The robots worked through the desert nights. The fibers caught their light. The spectra piled up, galaxy by galaxy. The map grew, until scientists had enough to do the thing they had built the whole machine for. They could compare the strength of the universe's push in the distant past to its strength today. For years, almost everyone expected the same boring, comforting answer. Dark energy would be constant, just as the Standard Model promised. The map would confirm Einstein's old constant and close the case. Then the first big batch of results came in. The team gathered to look at what the universe had been hiding, and the answer on the screen was the one thing nobody was ready for. The first full year of DESI data was ready. Years of building, calibrating, and collecting had finally produced enough of the map to test the big question. Scientists from all over the world gathered to see what the universe would say. They had a clear expectation. The data would show dark energy as a constant. The Standard Model had passed every test for decades. The smart bet, the safe bet, the bet almost everyone made, was that this map would simply confirm what they already believed. Dark energy, steady, case closed, a triumph of careful measurement. The team fed in the data. Millions of galaxies, mapped across billions of years, the cosmic ruler measured at distance after distance. The computers compared the strength of the universe's push in the ancient past to its strength in more recent times. Everyone waited for the flat line, the boring straight result that meant the constant was real. The result was not a flat line. The data hinted that dark energy was not the same across time. In the distant past, the push appeared to have been stronger. In more recent eras, it looked weaker. The mysterious force that drives the entire universe apart seemed to be fading, slowly losing its strength as the cosmos aged. For a moment, this had to feel like a mistake. The Standard Model was supposed to be bulletproof. Dark energy as a constant was the foundation everyone stood on. And here was the most powerful cosmic mapping machine ever built, quietly suggesting that the foundation was wrong. The room understood what they were looking at. If dark energy is changing, then it is not Einstein's constant. It is not a fixed property of empty space, the same forever. It is something dynamic, something alive in a way nobody had confirmed, a force with its own history that grows and shrinks over cosmic time. Scientists are careful people, and for good reason. One surprising result does not topple a model that has worked for 30 years. They did what good researchers always do. They questioned themselves first. Could there be an error in how the galaxies were measured? Could some unknown effect be faking the signal? Could the way they combined DESI data with other surveys be tilting the answer? They checked. They reran the analysis. They combined DESI's map with other independent measurements, including the light from those same exploding stars that started this whole story back in 1998. The hint did not vanish. If anything, pulling more data together made the signal of fading dark energy a little stronger, not weaker. This was bigger than a single odd reading. It was a crack running straight through the Standard Model of the universe. The simplest, most comforting idea, that dark energy is steady and the cosmos will expand smoothly forever, was suddenly on shaky ground. Word spread fast through the world of physics. Some scientists were thrilled. A changing dark energy would mean new physics. a doorway to deeper laws nobody had written yet. Others were cautious, even worried. A result this big needed far more proof before anyone could call it certain. But the genie was out. The most detailed map of the cosmos ever built was whispering that the engine of the universe is not constant. It is winding down, and once you accept that the push might be fading, a terrifying new question opens up. By how much has it already dropped? And when exactly did the most powerful force in existence begin to die? The hint from Deci was clear enough to shake the field. Dark energy did not look steady. It looked like it was changing. So scientists pushed harder on the next obvious question. If the push is changing, what does the change actually look like? Is it slowly growing, or is it fading away? The data pointed in one direction, and it was the unsettling one. Dark energy appeared to be weakening. This flips the old story on its head. For years, the picture was simple. Dark energy is constant, and as the universe expands and matter thins out, the push keeps winning more and more, accelerating the cosmos faster forever. The future was a runaway, faster, emptier, colder, with no end. A weakening dark energy rewrites that future completely. If the push is fading, then the acceleration is not guaranteed to last. The force tearing space apart might be running out of steam. The thing everyone assumed would dominate forever may have already passed its prime. To picture how strange this is, go back to the tug of war between gravity and dark energy. Gravity pulls everything together. Dark energy shoves everything apart. For billions of years after the Big Bang, matter was packed close, gravity ruled, and the expansion slowed. Then space spread out, matter thinned, gravity weakened, and dark energy took over, speeding the universe up. That much scientists were already sure of. The new twist is what happens next. If dark energy were a true constant, it would simply keep winning, forever and ever, no contest. But a weakening dark energy changes the whole match. The push that took the lead might be losing power even as we watch. Its victory might not be permanent at all. This is why the discovery hits so hard. It is one thing to not understand a force. It is another to learn that the force is unstable, shifting under your feet, behaving like something with a lifespan instead of a fixed law of nature. A constant is reliable. You can predict it. A changing, fading force is wild and unpredictable, and it makes the entire future of the universe an open question again. Scientists describe dark energy using a number that captures how it behaves over time. For a perfect constant, that number sits at one exact value and never moves. The Deci data suggested the number was not sitting where it should. It looked like dark energy had behaved differently in the past than it does now, drifting away from the steady value the standard model demanded. That drift is everything. A constant does not drift. The moment dark energy shows any change across cosmic time, it stops being Einstein's tidy fudge factor and becomes something far stranger, a force with moods, with a rise and a fall, with a story that is still being written. And the data did not just say the push was changing in some vague way. It pointed to a specific, eerie pattern. Dark energy seemed to have grown stronger early on, climbing as the young universe aged until it hit a peak. Then, at some point in cosmic history, it stopped climbing. It turned over and it began to fall. That means somewhere out there in the timeline of the universe, there is a moment, a high point. The instant when the most powerful force in all of existence reached its maximum strength and then, for reasons nobody understands, started to die. Scientists looked closer to find that turning point, and what they calculated about when it happened and how far the push has already dropped made the whole thing feel disturbingly real. If dark energy is fading, then somewhere in the history of the universe there is a peak, a single high point where the push was at its strongest before it began to slip. Scientists dug into the data to find it, and the picture that came back was strangely specific. The numbers suggested that dark energy reached its peak strength when the universe was around 70% of its current age. Before that point, the push was climbing. After it, the push began to fall. We are living on the downhill side of that curve, in the long, slow decline of the force that runs the cosmos. Put that in plainer terms. The universe is about 13.7 billion years old. 70% of that lands roughly 9.5 billion years after the beginning. So, for billions of years, dark energy grew stronger and stronger, building toward its high point. Then it crested, like a wave reaching its tallest moment, and started rolling back down. We did not arrive in time to see the peak. We arrived for the fading. And the fading is not some tiny hair-splitting amount you would need a supercomputer to notice. The data suggests dark energy today is around 10% weaker than it was at its strongest. 10% of the most dominant force in the universe has already drained away. 10% might not sound like much, but this is the force that controls the fate of everything. It is the thing deciding whether the cosmos expands forever or someday collapses. A 10% drop in something that powerful is not a rounding error, it is a trend. And a trend, once it starts, tends to continue. That is the part that turns a curious result into something genuinely frightening. If dark energy peaked and has already fallen 10%, the obvious question is, where does it stop? Does it level off at some new, lower value and hold there? Does it keep sliding down slowly? Or does it keep falling, past zero, into something far stranger? Nobody knows. The curve has a clear past and a deeply uncertain future. We can see that the push grew, peaked, and started to drop. We cannot yet see where the drop leads. Think of a ball thrown straight up. It rises, slows, reaches its highest point, then begins to fall. If dark energy is following a curve like that, we are watching it just after the top, in the early part of the fall. The terrifying thing is that a ball thrown up always comes back down all the way. We do not know yet whether dark energy will do the same, or whether it will catch itself partway and hold. Everything hangs on that unknown, a force that fades a little and then steadies leaves us with a strange but survivable universe. A force that keeps fading, all the way down, and then past zero, leads somewhere much darker. The difference between those two futures is the difference between an empty, drifting cosmos and a violent, crushing end. The decimap could show that the decline had started. It could measure how far the push had fallen. What it could not do was explain why. Why would a fundamental force of nature, something we expected to be a fixed law, rise and fall like a living thing? What could possibly be behind a force that changes its mind across billions of years? To chase that answer, scientists had to stop looking out at the giant galaxies and start looking in at the smallest pieces of matter that exist. And the place leading that hunt was not an observatory at all. It was a ring buried under the border of two countries. The biggest clue to the largest mystery in the universe might be hiding in the smallest place imaginable. To understand a force that spans the whole cosmos, scientists turn to the world of particles, the tiny building blocks beneath atoms. And the center of that hunt sits under the ground near Geneva, at a lab called CERN. CERN is the largest particle physics laboratory on Earth. Buried beneath the border of Switzerland and France runs its most famous tool, a circular tunnel about 17 miles around, where particles are flung close to the speed of light and smashed together. By studying the wreckage of those collisions, scientists pull apart the fabric of matter to see what reality is truly made of. For decades, the work at CERN focused on the particles we know, the pieces that build ordinary matter, the small 5% of the universe we can see and touch. That work paid off. It confirmed the existence of particles that complete our picture of how matter and forces fit together. But that picture only ever described the visible sliver. The other 95%, the dark matter and dark energy that dominate everything, stayed completely outside it. So the scientists at CERN set their sights on the dark side. If dark energy and dark matter are real, and they clearly are, then maybe they are made of particles too. Particles nobody has ever caught. Particles that do not fit into the known rules. A hidden family of matter and forces, sitting right alongside our own, almost completely cut off from it. This hidden family has a name. Scientists call it the dark sector. The idea behind the dark sector is both simple and dizzying. Everything we understand, every particle, every force, might be only half the story. There could be a whole second set of particles and forces that we have missed, not because they are far away, but because they barely interact with our kind of matter. They could be passing through you right now, through the Earth, through everything, almost never bumping into anything we can detect. Picture two crowds walking through the same train station, somehow sharing the same space, yet almost never touching. One crowd is everything we know, the atoms and light and forces of ordinary life. The other crowd is the dark sector, moving through the same reality, ghosting straight through us. We have spent all of history studying one crowd while the other walked beside us, unseen. If dark energy is a fading force with its own behavior, the dark sector is the natural place to look for its source. Maybe dark energy is not the energy of empty space at all. Maybe it is the work of some dark sector particle or force, something that can change over time, something that can rise and peak and fall. Exactly the kind of behavior the decimap hinted at. The trouble is obvious. If these particles barely touch our matter, how do you catch one? You cannot see them, cannot hold them, cannot trap them in a normal detector. They slip through everything. Hunting the dark sector is like trying to catch a ghost that walks through walls, that leaves no footprints, that you only suspect exists because of the way distant things move. CERN decided to try anyway, and the first weapon they built for the hunt does something that sounds almost reckless. It fires a beam of high-speed particles straight at a wall, then watches for the one thing that should be impossible. The experiment is called NA-64, and the way it hunts for the dark sector sounds almost too simple to work. It fires a beam of high-energy electrons straight into a thick block of material, a kind of wall, and then it watches what comes out the other side, or more importantly, what does not. When an electron slams into that wall at nearly the speed of light, normally all of its energy has to go somewhere we can account for. The collision sprays out a shower of particles and energy, and detectors carefully add it all up. Energy in should equal energy out. That is one of the oldest and most trusted rules in all of physics. Energy never just vanishes, unless it does. The whole point of NA-64 is to catch energy disappearing. The scientists fire in an electron, measure its energy exactly, then measure everything that comes out of the collision. If the books balance, nothing strange happened, but every so often, they hope to see a collision where some energy goes missing, where the total coming out is less than what went in, with no ordinary particle to explain the gap. That missing energy would be the fingerprint of something escaping into the dark sector. The idea is that when the electron crashes into the wall, it might occasionally create a dark sector particle, something that carries away energy and then slips out of the detector without ever interacting again. The machine would never see the particle itself. It would only see the hole it left behind, the missing energy that should have been there and was not. This is detective work at its purest. You never catch the thief in the room. You just notice that something is gone, and from the size and shape of the gap, you figure out what must have taken it. NA-64 is built to notice the cosmic equivalent of a missing wallet, then work backward to the ghost that walked off with it. The particular ghost they are chasing has a name. It is called the dark photon, and it might be one of the most important things in the universe that nobody has ever seen. To understand the dark photon, start with the regular photon, which is just a particle of light. The ordinary photon is the messenger of one of nature's forces. It is what carries light, what lets your eyes work, what makes electricity and magnetism possible. Whenever two charged particles push or pull on each other, they are really tossing photons back and forth. The photon is the go-between for the visible world. The dark photon would be its hidden twin, a messenger particle like the photon, but one that belongs to the dark sector instead of our world. If it exists, it would act like a secret doorway, a rare connection between our kind of matter and the hidden kind. Most of the time, the two worlds ignore each other completely, but through the dark photon, every now and then, they might whisper across the gap. Find the dark photon, and you find the bridge. You prove the dark sector is real, and you open a path to studying it directly, maybe even to understanding what dark energy and dark matter truly are. So Na 64 fires its electrons, night after night, watching for energy that refuses to add up. It is a patient, stubborn hunt for an absence, for a gap in the books that points to a whole hidden half of reality. Catching that missing energy would be a landmark, but it is only one of CERN's weapons in this fight. Another experiment is hunting an even stranger target, using a telescope that stares at the sun yet is built to never actually see its light. While one experiment at CERN fires particles at a wall, another points itself at the sunday. It is a telescope, but a very strange one. It is built to track the sun across the sky with great care, and yet it is designed never to actually see the sun's light at all. The instrument is called CAST, the CERN Axion Solar Telescope, and to understand it you have to understand what it is hunting. Its first target was a particle called the axion. The axion is a hypothetical particle, meaning scientists have strong reasons to think it might exist, but nobody has ever caught one. It was first dreamed up to fix a separate puzzle in physics, an oddity in how one of nature's forces behaves. The math worked out cleanly if a tiny, lightweight, almost ghostly particle existed to balance things. That particle was the axion. It would be incredibly light, far lighter than the particles inside an atom, and it would barely interact with anything, slipping through matter like it was not even there. Axions quickly became a leading suspect for dark matter. If the universe is full of these tiny, nearly invisible particles, they could provide the hidden mass that holds galaxies together. So scientists wanted to catch one badly. The problem, as always with the dark side, is that something that barely interacts is brutally hard to detect. This is where CAST gets clever. Theory suggests that an axion, under the right conditions, can turn into a particle of light when it passes through a strong magnetic field. A ghost particle slips into a powerful magnet and transforms into something a detector can actually see. So, CAST uses a giant magnet, a huge one borrowed from the technology built for CERN's main collider, and points it straight at the sunday. Why the sun? Because the sun, with its blazing core, should be a factory for axions. If axions are real, the sun should be pouring them out constantly, a steady stream pouring straight through space and through the earth and through you, unseen. CAST aims its magnet at the sun and waits. If a solar axion enters that magnetic field, it might flip into a tiny flash of light, and the detector at the far end would catch it. That is why the telescope tracks the sun but never needs to see its light. It is not looking for sunlight at all. It is looking for ghosts streaming out of the sun, ghosts that only reveal themselves by turning into a faint glimmer inside a magnet. The sun's ordinary light is beside the point. CAST wants the invisible particles hiding inside the sunshine. For years, CAST hunted axions this way, patiently aiming at the sun, watching its magnet for the faint signal of a particle that flipped into light. It became one of the most sensitive axion hunts ever built. Then, something interesting happened. Scientists realized the same machine, the same magnet pointed at the same sun, might be able to hunt something else entirely. Not just axions for dark matter, but a different particle tied directly to dark energy itself. A particle so strange that it changes its own weight depending on where it is, heavy in a crowded lab and feather light in the emptiness of deep space. They called it the chameleon, and it carries an idea that could explain why dark energy rises, peaks, and fades. It suggests dark energy is not a constant at all, but a brand new force of nature, a fifth force we have never named. The chameleon is one of the strangest ideas in modern physics, and it carries a claim that would rewrite the rulebook. It says, dark energy might be a brand new force of nature. Right now, scientists know of 4 forces that run everything. Gravity, which pulls planets and people. Electromagnetism, which makes light and electricity. Then 2 forces that work deep inside atoms. holding their cores together and letting them break apart. 4 forces. That is the whole list. Every push and pull you have ever felt traces back to one of them. The chameleon idea says there is a fifth. This fifth force would be carried by a particle, the chameleon, the way light is carried by the photon, and this new force would do one specific job. It would push space apart. It would be dark energy, not as the dull energy of empty space, but as an actual force with its own particle, its own rules, and its own ability to change over time. That last part matters more than anything. A force carried by a particle can shift and evolve. It can be strong in one place and weak in another. It can rise and fall. The decimap hinted that dark energy grew, peaked, and started to fade, behaving like something alive. A constant property of empty space cannot do that. A force with its own particle can. The chameleon offers a way for dark energy to have a story, a history, a rise, and a decline. But a fifth force runs into a brutal problem right away. If there really were a new force pushing things around, we should have noticed it by now. Forces leave fingerprints. We have measured gravity to insane precision. We have tested electromagnetism in millions of experiments. A fifth force, strong enough to drive the entire universe apart, should be obvious in a lab. We should trip over it constantly. We do not. In every careful experiment on Earth, there is no sign of a mysterious fifth push. The force that supposedly controls the fate of the cosmos goes completely missing the moment scientists try to measure it up close. That is a serious contradiction. A force can drive galaxies apart across billions of miles, yet vanish entirely inside a laboratory. Most ideas would die right there, killed by that single problem. The chameleon survives because of one clever, almost sneaky trick built into its design. The chameleon hides. The whole idea is named after the lizard that changes its color to blend into its surroundings. This particle changes something even stranger than color. It changes its own weight, its own strength, depending on where it is. In a crowded place, packed with matter, the chameleon becomes heavy and weak and shy, tucking itself away so well that no experiment can spot it. In an empty place, with almost no matter around, it becomes light and strong and bold, stretching out to push space apart. That solves the contradiction in one move. On Earth, surrounded by dense matter, the chameleon goes heavy and hides, which is why we never feel a fifth force in the lab. Out in the vast emptiness between galaxies, where matter is thin, the chameleon goes light and powerful, and there it does its work, prying the cosmos apart as dark energy. It is a force that becomes invisible exactly where we live and only wakes up where we cannot easily reach. Which raises a maddening question. If this thing deliberately hides wherever there is matter, how could anyone ever catch it? The chameleon's hiding trick is clever, and it comes down to one simple rule. The more matter is around, the heavier and weaker the chameleon becomes. Picture it like this. Imagine a person who shrinks and goes silent the instant they walk into a crowded room, then grows huge and loud the moment they step into an empty field. That is the chameleon. Crowd it with matter, and it curls up small, heavy, and almost impossible to notice. Give it open space, and it swells, lightens, and starts to push with real force. On Earth, the chameleon is in the most crowded room imaginable. Our whole planet is packed solid with matter, atom on atom, all the way down. To a chameleon, Earth is a dense, suffocating place. So here, it goes heavy. A heavy chameleon barely moves and barely pushes. Its fifth force shrinks down to almost nothing, far too faint for any normal experiment to feel. That is why no one trips over a fifth force in daily life. The chameleon is hiding inside its own weight. Now travel out into deep space, into the enormous gaps between galaxies. Those gaps are emptier than anything you can picture. There is so little matter that some regions hold barely a few atoms in a space the size of a city. To a chameleon, that emptiness is freedom. Out there, it goes light. A light chameleon stretches far and pushes hard. Its fifth force wakes up and spreads across the void, shoving galaxies apart. That push, summed across the vast empty oceans between galaxies, becomes the dark energy driving the universe to expand. So the same particle behaves like two completely different things in two different places. Near matter, it is a heavy, hidden nobody. In empty space, it is a powerful engine of cosmic expansion. The crowd decides which face it wears. This even explains the rise and fall that Deci spotted. Long ago, the universe was smaller and more crowded. Matter was packed closer together everywhere. In a denser cosmos, the chameleon would have behaved differently than it does today, its strength tied to how spread out everything was. As the universe expanded and thinned, the average crowding dropped, and the chameleon's push would shift in response. A force whose strength depends on the density of its surroundings is a force that naturally changes as the universe grows. It can climb, peak, and fade, matching the eerie curve the data hinted at. That is what makes the chameleon so tempting. It does not just offer dark energy as a fifth force. It offers a fifth force that automatically evolves, that hides where we live and roars where we cannot easily look, that rises and falls as the cosmos stretches. It threads through every strange clue at once. The catch is the same one that always haunts the dark side. A particle built to hide near matter is a nightmare to catch, because every detector we own is made of matter. The moment a chameleon comes close to our equipment, it goes heavy and shy and slips away. We are trying to photograph something that turns invisible the instant we point a camera at it. To corner a thing like that, scientists had to get fiendishly clever. And the trap they built relies on a sensor so unbelievably delicate that it can feel a nudge the size of the tiny core of a single atom. Catching a chameleon means beating its hiding trick, and that takes equipment pushed to the very edge of what is possible. The same CAST telescope that hunts axions can hunt chameleons too, using its giant magnet to coax these shy particles into revealing themselves. If a chameleon streaming from the sun passes through that powerful magnetic field, it might convert into a faint flicker of light a detector can catch. The same basic trick used for axions. But chameleons are even slipperier than axions because of their hiding behavior. So scientists added other traps, and one of them is a marvel of delicacy that almost sounds made up. The idea is to look for the chameleon's force directly. If a chameleon force exists, it should give the tiniest possible push to a small object placed in just the right setup. Not a push you could ever feel. Not a push that would move a grain of sand you could see. A push so impossibly small that detecting it requires a sensor more sensitive than almost anything humans have ever built. So engineers built exactly that. They created a sensor with a membrane, a thin skin stretched tight, so delicate that it can detect a movement the size of the core of a single atom. Let that sink in for a second. An atom is already so small that millions of them could line up across the width of a human hair. And the core of an atom, its nucleus, is far tinier still, a speck buried at the center of that already invisible thing. This sensor can feel a nudge that small. It is like building a scale so sensitive it could weigh a single fingerprint left on a mountain, or a microphone so sharp it could hear one grain of sand land on the far side of a football field. The precision is almost unreal. Engineers had to fight constant tiny vibrations, stray heat, and faint magnetic whispers. Anything that could fake the signal they were hunting. They had to silence the entire world around the sensor, so the only thing left to feel would be the ghostly touch of a force that might not even exist. This is the strange shape of the whole search. To find the force that controls the biggest thing there is, the entire universe, scientists build the most sensitive small instruments imaginable and watch for the faintest possible flinch. The largest mystery in existence might announce itself as a twitch smaller than an atom's heart. So far, the flinch has not come. CAST and its cousins have searched, and they have not yet caught a chameleon, or an axion, or a dark photon. Every hunt has come back empty, but empty does not mean failure. Each search that finds nothing rules out a range of possibilities, narrowing the hiding spots, closing the net. Scientists now know more about where these particles are not, which slowly tells them where to look next. The hunt continues, patient and stubborn, on the smallest scale humans can reach. And whether or not the chameleon turns out to be real, the idea behind it has already cracked open something deeply unsettling about reality itself. Because if dark energy can change, if the push can rise and fall, then the emptiness it lives in, the vacuum of space we always pictured as fixed and stable, might be quietly shifting beneath everything we know. For a long time, scientists treated empty space as the one truly reliable thing in the universe. Matter moves, stars burn out, galaxies drift, but the stage they all sit on, the vacuum itself, was supposed to stay perfectly still and stable. The fixed backdrop, the one thing you could count on, never to change. A weakening dark energy threatens that idea at its root. Remember, the simplest explanation for dark energy was the energy of empty space, a fixed amount baked into every speck of the vacuum. If that energy is constant, then the vacuum is stable, sitting calmly at its lowest, most settled state, like a ball resting at the bottom of a valley. It has nowhere lower to go. It stays put forever. But the DESI data hints that dark energy is changing. And if the energy of the vacuum is changing, then the vacuum is not resting at the bottom of anything. It is sliding, slowly. Across billions of years, the empty space that holds the universe together might be drifting from one state toward another. Picture that ball again. Instead of resting safely at the bottom of a deep valley, imagine it parked on a gentle slope or in a shallow dip partway up a hill. It looks calm, it looks settled, but it is not truly at the lowest point. Given enough time, it could roll. The vacuum of space might be exactly like that ball, sitting in a spot that seems stable, but is really just a pause on the way down to somewhere else. This is a deeply uncomfortable thought, because everything we are is built on top of that vacuum. The particles in your body, the forces holding your atoms together, all of it plays out against the backdrop of empty space. If that backdrop is shifting, then the rules written on it might shift too. A stable vacuum means stable laws of physics. A sliding vacuum means the laws themselves could, in principle, slowly change. Scientists take this seriously enough to have a name for the nightmare version of it. They wonder whether the vacuum could one day drop suddenly to a lower, more stable state. The way our gently parked ball might finally roll off its slope and crash to the true bottom. If that ever happened, the change would spread outward at the speed of light, rewriting the rules of physics as it went, and nothing inside it would survive in any form we would recognize. Now, there is no sign that such a sudden drop is coming. This is a possibility buried in the math, not a forecast. The shifting hinted at by dark energy is gentle and slow, measured across billions of years, not a switch about to flip. The universe is not on the edge of blinking out tomorrow, but the deeper point stands, and it is humbling. We always assumed the vacuum was the solid floor under everything, the one fixed thing. A changing dark energy suggests that floor might be the surface of a very slow ocean, gently rising and falling beneath our feet. The stage is moving, the background is alive. The emptiness we trusted to stay still may be the most quietly unstable thing of all. And if the vacuum can drift, and the forces written on it can drift with it, then a strange and personal question follows. Could the matter inside you, the very atoms you are made of, be slowly changing too? Here is a thought that sounds like science fiction, yet falls straight out of the idea that dark energy can change. If the energy of empty space is shifting, then the forces that hold your atoms together might be shifting along with it. To see why, you have to know how your atoms stay glued. Every atom has a tiny core packed with particles bound by one of nature's strongest forces, the force that holds atomic cores together. The strength of that force is set by certain fixed numbers, the deep settings of physics. Those settings decide how tightly your atoms hold, how stable matter is, whether the stuff you are made of stays solid and reliable. For all of history, we assumed those settings were carved in stone, Constants, numbers that have always been the same and always will be, everywhere, for all time. The mass of a particle, the strength of a force, fixed values you could trust completely. A shifting vacuum puts a crack in that certainty. Some physicists connect the changing energy of the vacuum to the very forces that govern atoms. If the vacuum is slowly sliding from one state toward another, then the deep settings of physics, the so-called constants, might not be perfectly constant after all. Across enormous stretches of time, they could drift by tiny amounts, nudged by the shifting emptiness underneath them. Think about what that would mean. The force binding the core of every atom in your body could be very slightly different in the far future than it is today. Not enough to feel, not enough to notice in a lifetime, or a million lifetimes. But over billions of years, a slow creep in the rules could change how matter behaves at the deepest level. In a universe like that, the atoms inside you are not eternal, fixed things. They are settings on a dial that is turning so slowly you can never catch it moving. Stable for now, yes. Solid for now, absolutely. But tied, in some hidden way, to the changing energy of the empty space around them. Now, calm down before you start worrying about your atoms falling apart. There is no evidence that this is actually happening on any scale that matters to a human or even to a planet or a star. Careful measurements show that the constants of physics have held remarkably steady for as far back as we can check. Any possible drift is so small that it stays purely in the realm of theory. Your atoms are not going anywhere. The point is not panic. The point is how far the cracks reach. A single strange result from a telescope in Arizona, a hint that one cosmic force is fading, ripples all the way down to the smallest, most personal level of reality. If dark energy can change, then maybe the vacuum can change. And if the vacuum can change, then maybe even the rules that build your body are part of a story still being written, rather than a finished law handed down forever. That is the quiet horror and the quiet wonder of it. We used to think we lived in a finished universe, with fixed rules and a fixed stage. The fading of dark energy whispers that we might live in an unfinished one, still settling, still shifting, still deciding what it wants to be. And some scientists push the idea even further, suggesting dark energy is not a built-in feature of space at all, but something the universe produces, like exhaust from an engine. Most explanations treat dark energy as something woven into the universe from the start, a built-in feature of space or a fundamental force. One bold idea flips that completely. It suggests dark energy is something the universe makes as it goes, a byproduct like exhaust pouring from an engine. To understand this, think about what happens when things get built. Across cosmic time, gravity has been pulling matter together into ever larger structures. Gas collapses into stars. Stars gather into galaxies. Galaxies clump into enormous clusters, the biggest assembled objects in existence, held together by gravity across distances that stagger the mind. Building those giant structures is a process, and processes generate waste heat. When an engine runs, it does useful work, but it also dumps energy out the back as exhaust. When you exercise, your body does work and throws off heat. This idea proposes that the universe is doing something similar on the grandest scale. As gravity assembles galaxies and clusters, the process produces a kind of leftover energy spread thin throughout space. That leftover energy, some scientists suggest, is dark energy. It is a wild reframing. In this picture, dark energy is not an eternal property of the vacuum and not a fifth force hiding in particles. It is the cosmic equivalent of the heat coming off a working machine, generated steadily as the universe forms its largest structures. The push driving everything apart would be the exhaust from everything coming together. This idea has a strange appeal because it could explain why dark energy changes over time. If dark energy is a byproduct of building structures, then its strength would depend on how fast the universe is building them. In eras when galaxies and clusters were forming rapidly, the cosmic engine would run hot, producing more of this exhaust energy. As that building slows, the exhaust would taper off. A force tied to construction would naturally rise while the universe is busy assembling, then fade as the great building project winds down. That matches the unsettling pattern Deci hinted at. Dark energy growing in the active, structure-building past, peaking, then declining as the cosmos matures and the pace of building drops. A constant property of space has no reason to behave that way. An exhaust generated by ongoing work does. The idea is far from proven. It is one of several competing explanations, a clever possibility rather than an established fact, and many physicists are skeptical. Pinning dark energy to the formation of structures requires the numbers to line up in ways that are not yet confirmed. But it captures something important about where the science is right now. The simple story, dark energy as a fixed constant, is wobbling, and into that wobble pour bold new ideas, each trying to explain a force that seems to live and change. What all these ideas share is a single break from the past. For decades, dark energy was treated as a steady, eternal thing, the same yesterday and forever. Now the leading questions all assume it might move. Is it a shifting vacuum? A hiding fifth force? The exhaust of a building universe? Different answers, same shocking starting point. The most powerful force in the cosmos is not the fixed law we thought it was. And whatever dark energy turns out to be, its behavior right now is already doing something almost unbelievable to the sky above us. It is pushing distant galaxies away from us, faster than light itself can travel. Here is something about the universe that sounds flat out illegal. Distant galaxies are moving away from us faster than the speed of light. You probably learned that nothing can travel faster than light. That is one of the most famous rules in all of physics, and it is true. No object can race through space faster than a beam of light. A spaceship, a particle, a signal, none of them can break that limit. So how can whole galaxies be fleeing faster than light without shattering the rule? The answer is a beautiful loophole, and it changes how you have to picture the whole cosmos. The galaxies are not moving that fast through space. The space between us and them is stretching. That distinction is everything. Nothing can move through space faster than light, but space itself has no such speed limit. Space can expand as fast as it likes, and dark energy is stretching space everywhere, all at once, in every gap between galaxies. Picture two ants standing on a giant rubber sheet, far apart. Neither ant is moving its legs at all. Now imagine the whole sheet stretching in every direction. The two ants are carried away from each other, even though neither one is walking. Stretch the sheet fast enough, and the ants separate faster than either could ever crawl. The galaxies are those ants. Space is the sheet. Dark energy is the stretching, and it is happening to every patch of empty space at once. Add up all that stretching across the unthinkable distance to a faraway galaxy, and the total speed of separation can blow right past the speed of light. The galaxy is barely moving through its own little patch of space, but there is so much expanding space between us that the gap grows faster than light can cross it. This has a haunting consequence. Some galaxies are now so far away, and the space between us is stretching so fast that their light can never reach us. It sets out toward us, but the space ahead of it expands faster than the light can swim through it, like a swimmer trying to reach shore against a current that pulls harder than they can stroke. That light will never arrive. Those galaxies have crossed a kind of horizon, sliding past the edge of everything we will ever be able to see. And it gets lonelier. As dark energy keeps stretching space, more and more galaxies cross that line. One by one, over billions of years, they slip beyond the reach of our telescopes forever. The observable universe, the part we can actually see, is slowly emptying out as its contents flee past the edge of visibility. If dark energy stayed constant or grew stronger, this emptying would continue without end, Far in the future, a civilization on some distant world might look up and see only their own galaxy, alone in a black sky, with no hint that billions of others ever existed. The evidence of the wider universe would have slipped away, carried off by the stretching of space, leaving them no way to know what they had lost. This is the future scientists feared under the old, constant dark energy, a cold, lonely, ever-emptying cosmos. And that future even has a name, an ending so bleak it took the field decades to make peace with it. For years, scientists believed they knew how the universe would end, and the ending was a slow, cold death. They called it the Big Freeze, and for a long time it was the leading guess for the fate of everything. The Big Freeze comes straight out of constant dark energy. If the push never fades, if it stays exactly as strong forever, then the universe expands faster and faster, with nothing able to stop it. Galaxies fly apart, space keeps stretching, and the whole cosmos coasts into a future that gets emptier, darker, and colder, with no end in sight. Walk through how it plays out, step by step, across spans of time so vast they make a human life feel like a single blink. First, the galaxies scatter. Dark energy carries them so far apart that, one by one, they slip beyond the edge of what anyone could see, exactly as we just described. The sky empties. Any future observers find themselves marooned in growing darkness, their neighbors gone. Then the stars begin to die. Stars run on fuel, and fuel runs out. Across unimaginable stretches of time, the existing stars burn through their supply and flicker out. New stars need raw material to form, and that material slowly gets used up. Star birth slows, then stops. The lights go out across the universe, one by one, with fewer and fewer replacements, until the era of starlight ends for good. After the stars, only their corpses remain, burnt-out cinders, dense, dead remnants, black holes. The universe becomes a scattering of cold, dark objects drifting through enormous, empty distances, with no fresh light anywhere. Even the black holes do not last. Over spans of time so long, the numbers lose all meaning. Black holes slowly leak away their energy and shrink until even they fade into nothing. Matter itself may break down over these endless ages, the particles that build everything slowly coming undone. What is left at the very end is almost pure emptiness, a cold, black, near-perfect void, stretched thinner and thinner forever, with the last faint warmth draining toward a final stillness. No stars, no galaxies, no light, no structure, just darkness, expanding into more darkness, approaching a temperature as close to absolute zero as the universe can get. Nothing happens, because nothing is left to happen to. That is the Big Freeze. The universe does not explode or collapse. It simply runs down, like a fire burning to its last ember, then to ash, then to cold. An ending not with a bang, but with an endless, silent fading. For decades, this was the consensus, the future written into the standard model. It is bleak, but it is also weirdly gentle, slow, quiet, distant beyond all imagining, so far off that it changes nothing about your life or your world. The universe would die of old age, peacefully, in the dark, after a run so long it dwarfs everything that has happened so far. Scientists made their uneasy peace with the Big Freeze. It was cold comfort, but it was comfort. The ending was known. Then Desi whispered that dark energy might be fading, and a fading force does not deliver a slow freeze. If the push that drives everything apart is weakening, then the whole ending changes. Because once dark energy starts to fall, it might not stop at zero. It might keep going into something that flips the entire fate of the universe upside down. Everything about the Big Freeze depends on dark energy staying positive, always pushing outward. The Desi hint breaks that assumption, and it opens a door to something far more violent. What if dark energy does not just fade, but keeps falling, all the way down past zero? into negative numbers. A negative dark energy would do the opposite of everything we have described. Instead of pushing space apart, it would pull it together. To feel why this is such a turning point, go back one last time to the eternal tug of war. Gravity pulls everything inward. Dark energy pushes everything outward. Today, the push is winning, which is why galaxies fly apart faster and faster. The whole future of the cosmos hangs on which side stays stronger. Now imagine the push, not just weakening, but switching sides. Imagine dark energy crossing zero and turning into a pull. Suddenly, there is no contest at all. Gravity, which has spent billions of years fighting the outward push, would have its old enemy change into an ally. Both forces would now pull in the same direction, inward, together. Gravity would wake back up and take command. This is the great reversal. For most of cosmic history, dark energy has been the boss, overpowering gravity, driving the endless expansion. If dark energy fades to zero and then goes negative, that reign ends. Gravity reclaims the throne it lost billions of years ago. And gravity has been patient. All that matter spread across the universe, all those galaxies flung far apart, would feel the pull strengthen and begin, slowly at first, to drift back toward each other. The expansion would stall. For a while, the universe might seem to hang in balance, neither growing nor shrinking. A strange pause at the top of its long climb. Then, the balance would tip. The galaxies that have spent 14 billion years racing apart would slow, stop, and start the long fall back inward. Run the movie of cosmic history backward, and you get the picture. Everything that flew apart, coming together, everything that spread out, drawing in, the universe that has done nothing but expand since the Big Bang would begin, for the first time, to contract. This is the moment that turns a curious bit of data into something genuinely chilling. A fading dark energy is interesting. A dark energy that crosses zero and flips negative is the trigger for the end of the universe by collapse. The same force that has been gently spreading the cosmos thin could become the force that crushes it back together. Scientists cannot yet say whether this will happen. The data hints that dark energy is weakening, but it does not prove the push will keep falling all the way past zero. It might fade a little and then steady out, leaving us in a strange, calmer universe that neither freezes fast nor collapses. The difference between those outcomes is the difference between survival and destruction on a cosmic scale. And right now, nobody can be sure which way the curve will bend. But if the push does flip, if gravity does retake control and the galaxies do begin to fall back inward, then the universe is headed for an ending that makes the cold, quiet, big freeze look almost peaceful. It is loud, it is hot, and it ends with everything that has ever existed crushed back into a single point. If dark energy flips negative and gravity takes back control, the universe begins to fall inward, and that fall has a name, the Big Crunch. It is the Big Bang run in reverse, and it is one of the most violent endings the cosmos could possibly have. It starts slowly. After the expansion stalls and reverses, the galaxies begin drifting back toward each other, gently at first, barely moving. But gravity feeds on closeness. The nearer things get, the harder gravity pulls, and the harder it pulls, the faster they fall. What begins as a slow drift becomes a slide, then a rush, then a headlong plunge. The contraction speeds up over billions of years, accelerating the same way a ball rolls faster as it drops. As the universe shrinks, everything that's spread out over cosmic history reverses. Galaxies that drifted far apart come racing back together, the vast empty gaps between them close. Galaxies that have lived alone for ages begin to crowd, then crash, smashing into one another in titanic collisions as the available space collapses around them. Then comes the heat. This is the part that makes the Big Crunch so brutal. When you squeeze something, it gets hotter. Squeeze the entire universe, and the temperature everywhere begins to climb. All the energy and matter that was spread thin across enormous distances gets packed into smaller and smaller space, and as it compresses, it heats up. The cold, dark cosmos starts to warm, then to glow, then to blaze. The night sky itself would change. For all of human history, space between the stars has been black and freezing. In the Big Crunch, that darkness would slowly fill with light and heat as everything compresses until the whole sky burns. We will come back to that terrible brightening because it is one of the strangest sights the end of the universe would offer. As the crush continues, the rising heat tears matter apart. Temperatures climb so high that planets would melt, then vaporize. Stars would be ripped open. Eventually, it gets so hot that even atoms cannot survive, breaking down into the raw particles they are made of. The orderly universe of stars and worlds and living things dissolves back into a searing, formless soup, the same kind of hot, dense state the universe began in. And the collapse does not stop there. Gravity keeps pulling, the temperature keeps soaring, and everything keeps compressing toward a single, unimaginable point. All the matter, all the energy, every galaxy and star and atom that ever existed, crushed together into something smaller and hotter than the mind can hold. Space itself shrinks toward nothing. Time, as far as we understand it, would reach its end. That final moment is the mirror image of the Big Bang. The universe began as an unbelievably hot, dense point that exploded outward into everything. The Big Crunch would be that point reforming, the entire cosmos falling back into the same kind of state it was born from, a beginning in reverse, a universe swallowing itself whole. Whether anything could come after, a new bang, a new universe rising from the ashes of the old, is pure speculation, far beyond what any data can tell us. What the science can say is that a fading, dark energy reopens this fiery ending as a real possibility. After decades, when the cold, big freeze seemed certain. And of all the horrors the Big Crunch would bring, one of the eeriest is what it would do to the night sky. Of everything the Big Crunch would do, one detail stands out as strange and almost beautiful in its horror. The night sky, which has been dark for the entire history of the universe, would slowly turn blindingly bright. To understand why, you have to understand why the sky is dark in the first place. Step outside at night and look up. Between the scattered stars, the sky is black. It seems obvious, but it is actually a deep clue about the universe. The darkness exists because space is enormous and mostly empty. Galaxies are flung so far apart that the spaces between them hold almost nothing, and their light is spread so thin across such vast distances that the gaps between stars stay pitch black. The universe is big enough and stretched enough that there is far more empty space than light to fill it. Now run the Big Crunch. As the universe collapses, all that spread out matter and light gets squeezed into smaller and smaller space. The galaxies that were flung far apart come crowding back together. The light that was spread thin across enormous distances gets packed tighter and tighter. The emptiness that made the sky dark starts to vanish. As the collapse rolls on, the gaps between galaxies shrink. More and more starlight crowds into less and less space. The sky, which has always been mostly black, begins to fill in. First, it would brighten faintly, a dim glow spreading between the stars. Then, as the squeeze intensifies, that glow would grow and grow and grow. Eventually, the entire sky would blaze. With galaxies crushed close together and all their light compressed into shrinking space, there would be no dark gaps left anywhere. Every direction you looked would be filled with light. The night sky would stop being a scattering of distant points against blackness and become a solid wall of blinding brightness, hotter and fiercer with every passing age. Picture it, a sky with no darkness left in it, no black between the stars, just light, in every direction, brightening towards something no eye could withstand. The cosmos would glow like the inside of a furnace, then like the surface of a star, as all the light that ever existed got packed into one shrinking, searing space. The same compression that heats the universe to destruction would also flood the sky with this terrible, growing glare. there is a strange symmetry to it. The universe began in a state of blinding heat and light, a hot, dense fire that cooled and spread out into the dark, star-spangled sky we know. The Big Crunch would reverse that journey exactly. The dark sky would fill back in with light, the cold would turn to heat, and the cosmos would return to the blazing brightness it was born in. The darkness we take for granted is just the long, cool middle of the story, the quiet stretch between two fires. No one would be around to watch the final brightening, of course. Long before the sky reached that killing glare, the rising heat would have destroyed every world and every living thing. The blinding sky would be the universe's last sight, with no eyes left to see it. This is the ending that a fading dark energy reopens. Yet before anyone declares the universe doomed to crush and burn, there is a giant, stubborn problem standing in the way of the whole story. The measurements that started all this do not fully agree with each other. Before you lie awake worrying about the universe collapsing into fire, you need to know about a problem that has been quietly tormenting cosmology for years. Scientists cannot even agree on how fast the universe is expanding right now. Two trusted ways of measuring it give two different answers, and the gap between them refuses to close. They call it the Hubble tension, and it is one of the deepest headaches in modern science. Here is the trouble. There are two main ways to measure the expansion rate of the universe, and they come at it from opposite ends of cosmic history. The first way looks at the early universe. Scientists study the oldest light in existence, a faint glow left over from shortly after the Big Bang, spread across the entire sky. By reading the patterns in that ancient light, they can calculate how fast the universe should be expanding today. It is like studying a baby photo of the cosmos and using it to predict how the grown-up should look now. The second way looks at the nearby, modern universe. Scientists measure the actual distances and speeds of relatively close galaxies, using bright markers like certain stars and exploding supernovas, the same kind of standard candles that revealed dark energy in the first place. This gives a direct, present-day reading of how fast things are flying apart right now. Both methods are careful. Both have been checked and rechecked for years by different teams using different tools, and both are trusted. The problem is that they disagree. The early universe method and the nearby universe method give expansion rates that do not match. The local measurement comes out faster than the early universe prediction says it should. That mismatch is the Hubble tension. It might sound like a small bookkeeping dispute, but it is not. It means our best understanding of the cosmos cannot fully explain its own expansion. Either one of the measurements has a hidden error nobody has found despite years of hunting, or, more thrillingly and more frighteningly, there is something missing from our picture of the universe. Some unknown ingredient, some new physics, hiding in the gap between the two numbers. This is exactly why scientists are so careful about the dark energy result. The universe has already shown them that it can hand back measurements that stubbornly disagree. The Hubble tension is a constant reminder that cosmic measurements are hard, that subtle errors can hide for years, and that a surprising number is not the same as a proven truth. Some scientists even wonder if the Hubble tension and the fading dark energy might be connected, two symptoms of the same missing piece. If dark energy behaves differently than the standard model assumes, it could ripple through the expansion calculations and help explain why the two measurements clash. A single new idea about dark energy might, just possibly, untangle both mysteries at once. That would be a stunning leap forward. Or the two puzzles might have nothing to do with each other, and chasing a link could lead nowhere. Right now, nobody knows. Both the Hubble tension and the weakening of dark energy sit in the same uncomfortable zone, real enough to take seriously, uncertain enough that no one can declare victory. That uncertainty is the heart of the whole story, and it has a precise meaning in physics. Before anyone can say dark energy is truly fading, the discovery has to clear a wall of proof that it has not yet reached. When scientists say they have hints that dark energy is weakening, they choose that word carefully. Hints, not proof. Because in physics, there is a strict, almost ruthless standard for what counts as a real discovery, and the dark energy result has not yet cleared it. That standard has a name: 5 sigma. To understand it, you have to know how scientists separate a real signal from a lucky fluke. Whenever you measure something, there is always a little randomness, a bit of noise that can make patterns appear by pure chance. Flip a coin 10 times, and you might get 7 heads, even though the coin is fair. That does not mean the coin is rigged, it just means random results can look meaningful when they are not. Sigma is a way of measuring how surprising a result is, how unlikely it would be to appear by accident. A low number of sigma means the result could easily be a fluke. A high number means a chance fluke gets less and less likely. 5 sigma is the gold standard for a discovery in physics. It means the odds of the result being a random accident are roughly 1 in a few million. Only when a finding crosses that 5 sigma line do physicists allow themselves to call it a true discovery. The famous confirmations in physics, the ones that make headlines and win prizes, all had to clear that bar. Scientists hold themselves to it precisely because nature has fooled them before, and because a claim about how the universe works needs to be rock solid before the world builds on it. The fading dark energy result has not reached 5 sigma. The hints from the cosmic map are strong enough to excite the entire field and strong enough to take seriously, but they sit below that strict threshold of certainty. The signal is there. It shows up across different datasets. Combining measurements makes it firmer, yet it has not crossed the line that would turn it from a tantalizing hint into a confirmed fact. By the rules of physics, it is not yet a discovery. It is a powerful clue waiting for more evidence. This is the discipline that makes science trustworthy, even when it is frustrating. It would be easy and exciting to shout that dark energy is dying and the universe is doomed to collapse. The careful scientists refuse to do that, because they have seen promising signals fade away before once more data came in. A hint at 3 or 4 sigma can vanish, revealed as a fluke or a subtle error, the moment a bigger dataset arrives. Until the dark energy result clears 5 sigma, the honest answer is that we have a stunning possibility, not a settled truth. The good news is that the proof is coming, one way or the other. The cosmic mapping machine keeps running, gathering more galaxies, sharpening the picture year after year. New surveys and instruments are joining the hunt, built to measure dark energy with even greater precision. Within the next several years, scientists expect to have enough data to either push this result past 5 sigma or watch it dissolve. The universe will be forced to give a clearer answer, so we sit at a genuine cliff edge of knowledge, holding a clue that could rewrite the fate of everything, waiting for the proof that will confirm it or kill it. And while we wait, the deeper meaning of it all settles in. Step back from the machines and the particles and the equations for a moment and ask the simple question: why should any of this matter to you, standing here, on one small planet, right now? It matters because dark energy is the single biggest factor deciding the long-term fate of absolutely everything. Not just Earth, not just the Sunday, every galaxy, every star, every atom that exists. The behavior of this one invisible force determines whether the universe drifts apart into cold darkness forever or comes crashing back together in fire. There is no bigger question about the future than this, and for the first time, we are gathering real data that bears on the answer. For most of human history, people guessed at the fate of the world through stories and beliefs, with no way to test them. We are the first generation that can actually measure the destiny of the cosmos with instruments, reading the fate of the universe from the light of distant galaxies and the gaps between them. That is a staggering thing to be alive for. The tools to study the end of everything did not exist a single human lifetime ago, and the picture those tools are painting is humbling. We learned that ordinary matter, the stuff of you and everything you can touch, is less than 5% of the universe. We learned that the rest is dark, invisible, and barely understood. Now we are learning that even the small part we thought we understood, the steady push of dark energy, might be shifting under our feet. Every layer of certainty we peel back reveals how much we still do not know. There is something freeing in that. Once the fear settles, we are tiny, made of rare scraps of stardust, clinging to a small world in a vast and shifting cosmos we barely comprehend. And yet we are the part of that cosmos that woke up and started asking questions. We built machines to map 11 billion years of history. We dug tunnels to smash particles and chase ghosts. We are the universe's way of trying to understand itself, and right now, in our lifetimes, that understanding is being rewritten. The fate of the universe will not be decided by anything we do. Whether it freezes or crunches will play out over spans of time so vast that all of human history is less than a flicker within them. None of these endings threatens you, or your children, or your civilization. They lie billions of years away, far beyond anything that touches a human life. What touches you is the wonder of it, the chance to live in the exact moment when our species figured out how to ask the biggest question there is and started, just barely, to glimpse an answer. You happen to be alive during the years when the steady, comforting story of the universe cracked open and a stranger, wilder story began to take its place. That is a rare kind of luck. The story is far from finished. The hints are real, but the proof is still out there, waiting to be gathered. And around the world, in deserts and tunnels and underground labs, scientists are closing in from every direction at once, building a net to finally catch the answer. The hunt for dark energy is no longer one experiment or one telescope. It has become a worldwide effort, with scientists closing in on the mystery from every possible direction at once. The cosmic mapping machine in the Arizona desert is just one part of a much larger net being drawn tight around the answer. Look at how many fronts the search runs on. The mapping machine keeps scanning the sky night after night, adding millions more galaxies to its three-dimensional chart, sharpening the measurement of whether dark energy is steady or fading. Every year it runs, its answer gets stronger and harder to dismiss. What started as a hint from 1 year of data grows firmer as the map fills in. At the same time, new instruments are joining the chase. Space telescopes built specifically to study dark energy are coming online, designed to survey enormous patches of sky and measure the expansion of the universe with a precision never possible before. These machines attack the same question from new angles, using different methods, so that the answer does not rest on a single technique that might hide a flaw. When several independent instruments, built by different teams using different tricks, all point to the same conclusion, that is when scientists start to trust it. Deep underground, the particle hunt grinds on. The electron firing experiment keeps watching for energy that vanishes into the dark sector. The solar telescope keeps aiming its great magnet at the sun, waiting for an axion or a chameleon to flip into a flicker of light. Other detectors around the world, buried under mountains and tucked into deep mines to hide from interfering noise, hunt for the faintest possible touch of dark matter and dark energy particles. Each empty result narrows the search, ruling out hiding places, telling the others where to look next. This is how the biggest discoveries actually happen. Not in a single dramatic flash, but in a slow tightening of the net, as many groups, many machines, and many methods converge on the same truth from different sides. One experiment alone can be fooled. A dozen experiments, all pointing the same way, become very hard to argue with. The strength of the dark energy story will come from this convergence, from astronomy and particle physics shaking hands on the same strange answer. And the pace is quickening. The questions that seemed impossibly out of reach a generation ago are now being measured directly. Whether dark energy is constant or changing, whether the dark sector is real, whether a fifth force hides in the emptiness of space. These were once pure speculation, the stuff of late-night wondering. Now they are research programs with budgets, instruments, and deadlines, expected to deliver real answers within years, not centuries. Somewhere in the next stretch of time, the net will close. The mapping machine will gather enough galaxies to push the fading dark energy result past the wall of proof, or watch it dissolve into noise. The particle hunters will catch their first ghost, or rule out whole families of ideas. Either way, the fog around the largest mystery in the universe is going to thin, and we will see further into the fate of everything than any humans before us. We are standing at the edge of that moment. The answer is not here yet, but it is coming, faster than ever, and when it arrives, it will reshape how we understand the beginning, the middle, and the end of the entire cosmos. So where does all of this leave us? Standing at the most exciting and unsettling crossroads in the history of cosmology, holding a clue that could rewrite the fate of the universe, waiting to learn which of three very different endings is real. Lay out the possibilities one last time, because the choice between them is staggering. The first ending is the big freeze. If dark energy turns out to be steady after all, or fades only slightly before holding firm, the universe keeps expanding into cold and dark forever. Galaxies drift apart, stars burn out, and everything slides toward a frozen, silent emptiness across spans of time beyond imagining. The ending we feared for decades. Quiet, cold, eternal. The second ending is the big crunch. If dark energy keeps fading, crosses zero, and turns into a pull, gravity wakes back up and drags everything inward. The expansion stops, reverses, and the entire cosmos comes crashing back together in rising heat and blinding light, collapsing toward a single searing point, the Big Bang in reverse, loud, hot, violent, an ending of fire instead of ice. The third possibility is the most honest one, something nobody has thought of yet. The history of cosmology is a graveyard of confident predictions that turned out wrong. We were sure the universe was static until it was expanding. We were sure it was slowing down until it was speeding up. We were sure dark energy was constant until the data started to wobble. Every time we felt certain, the universe revealed a deeper layer we had missed. The real fate of everything might be something we do not yet have the imagination to picture, waiting in physics we have not discovered. That is the thrilling, humbling truth at the center of all this. We have just learned that the most powerful force in existence, the thing that decides the destiny of the entire cosmos, may not be the fixed and steady law we believed it to be. It might be alive in a way, rising and peaking and fading, carrying the future of the universe with it as it changes. And we are the ones who get to find out, not through guesswork or stories, but through real machines, reading real light, gathering the evidence that will finally tip the answer one way or another. The cosmic map is growing. The particle hunters are closing in. New telescopes are opening their eyes. Within years, the hints will harden into proof or crumble into noise, and we will know far more than we do tonight about how all of this ends. Until then, the question hangs over everything. The biggest question there is: freeze, crunch, or something stranger than both? A universe that drifts into darkness, or collapses into fire, or surprises us one more time with an ending no one saw coming. The force that will decide is invisible, silent, and woven into every empty inch of space around you, including the space in this very room. It has been steady for billions of years. Now, for the first time, we have caught it changing, and the story of what that change means and where it leads is only just beginning to be written. The universe is keeping its biggest secret a little longer, but we are closer than we have ever been to making it talk.